Continuing the discussion about efficiency, what I had my students do in lab for the past few years, which we can't do now, is to build something called a solar suitcase, which was kind of neat. What this is basically it's a big battery and some other equipment that is all wired together, something called a charge controller that helps to regulate the battery. And there's also a few LED light bulbs that look like regular light bulbs that you plug in at your house, but they're actually DC. They run off batteries, 12-volt batteries. And with this suitcase, what we could do is we could put the solar panel on it and charge the battery, and then use the battery to run things at night in places where there isn't electricity available. Could be our house, too, if there's a power outage. So these were solar suitcases that my students would wire up and then test and then run and make sure that the battery was being charged by the solar panel and see light bulbs turn on from energy collected by the solar panel through the battery. And that was a fun thing, and it's neat because with this technology, it distributes the energy generation so that you don't have to rely on the power line to get the energy to where you want it. Of course, there's limitations. Your batteries can only be so big, but it shows a small example of what it's like to be independent with energy. If you have something like this, maybe with more batteries, you could perhaps charge them during the day and run them at night, or run them when it's cloudy, and still have enough energy as long as it got sunny every so often to recharge everything again. So these are the solar suitcases. And my house actually has solar panels, but they're not independent. If the power goes down, my house won't keep running off the solar panels because of the way that they're run and the fact that they put energy directly into the power lines that we all use. And for safety reasons, I'm not able to use the energy directly from my solar panels in my house. But I am generating energy that everybody uses, including myself. So I am actually an energy producer by living where I do and having solar panels on my roof. Now we're going to talk a little bit more about power and energy. How are they related to each other? And as I said at the end of last week, power in watts is equal to the current in amps times the voltage in volts. And you'll see, we'll look at units later, and you'll see that actually comes out to power in watts. It's the same power in watts that we learned in first semester physics, which if you remember, power is energy divided by time. Energy is in joules, which is Newton times meter. So kilogram meter squared per second squared is the unit of energy. And if you divide that by seconds, you'd have kilogram meter squared per seconds cubed is the unit of power, which is the watt, which is also a joule per second. It's the same thing whether it's electric or mechanical systems, same units. And we'll look at those more later. But if you simply multiply current in amps times voltage in volts, you get power in watts. And so you can figure out how much power, and we say power is being dissipated, because if a light bulb's producing a certain amount of power, most of it is leaving as heat, some of it's leaving as light, but the fact is it's leaving, it's being dissipated, it's going away from the circuit. Resistors also dissipate power, they just dissipate it as heat. So that is the meaning of power loss or power being dissipated. It's going away to something else. It could be becoming heat, or it could be a motor turning something else. So it's providing power that's giving something else energy at a certain rate, a certain amount of time, a certain amount of energy goes into something, like a drill or something you're spinning, you're giving it energy and causing it to have more energy every second. That would be a power transfer. So here are some of the units that we've been discussing currently and in the past. Power is this unit here. Here's the unit of watts. Current is unit of amps, symbol A. Voltage is volts, symbol V. Resistance is ohms, has the symbol capital omega. It's a Greek symbol. We also talked about energy being joules, and last semester also energy is the watt hour. We'll talk about the watt hour. It's another unit of energy. Power times time is energy, the watt hour. And sometimes you'll see, if you look on your batteries and you have magnifying glass or something, or really good eyes, you'll see that it tells how many amp hours the battery provides. That means the more current the battery is providing, the quicker it's going to run out. So if a battery, for instance, is able to supply 1 amp hour, That means whatever voltage it's at, it could provide 1 amp of current for an hour. And if you multiply the amp hour by voltage, you'd get watt hours, which is the amount of energy the battery actually has. There's a certain amount of energy that's stored in a battery. And if you recall from first semester physics, energy is force times distance. So that's the mechanical unit. And we use newtons rather than pounds, but pound is the English unit of force, and newton is the metric unit of force. Multiply that times the distance in either feet, if you're using the English units, or meters if you're using the metric units. And you have foot-pounds or newton meters, which is what we use, newton meters. And a newton meter, as we said, is a joule. It's the basic SI unit of energy. And here's a way you can do it's simply a calculation of multiplying two things. So this should actually be 2 foot-pounds, not 1 foot-pound. But if you multiply 2 pounds times 1 foot, you'd get 2 foot-pounds. It's a unit of energy. Similarly, if you had 2 newtons that you're exerting a force on something and you exerted that force over a distance of 1 meter, that would be 2 newton meters, would be the amount of energy that you expended in doing that. And you could, here's just a couple of other examples where you're simply multiplying the force times the distance. I prefer using newtons and meters, but this is the English units. And a foot-pound, as this box shows, is a little bit more than a joule. And joule is the basic unit, Joule, basic unit of energy that we talked about in first semester physics, that we will continue to use along with the watt hour and the kilowatt hour. And of course, power is the rate at which energy is being used or produced. It's measured in watts. Some examples, you see it on your light bulbs. It tells you it's a 4-watt LED lamp, maybe a 100-watt light bulb you could find. Your hair dryer is probably 1,000 watts. It's producing a lot of heat, dissipating a lot of heat. That's the stuff that helps dry your hair. It's also blowing it. So that takes a lot of energy to do that every second, 1,000 joules per second. Power plant production, you'll see things like megawatts, gigawatts. If you have a small solar panel, I have one in the physics lab, it's a 35-watt solar panel. That is all unit of power. It tells you how many joules are produced per second, or I should say converted per second from something else. Electric energy is also measured in joules, and electric power is also measured in watts. Or watt hour. Energy can also be measured in watt hours. I said power is measured in watts. Energy is power times time. Or power, if you like, is equal to energy divided by time. Power is in watts. A watt is a joule per second. So if you multiply the number of watts, so let's say you have a 100-watt light bulb, and it's burning for an hour, it's going to have consumed 100 watt hours of energy. If that same light bulb is lit for 2 hours, it's going to burn 100 watts times 2 hours, or 200 watt hours. So the longer something is running, the more energy it's going to use. That makes sense. The more watt hours it's going to have used. And we really already said this. And here's some more examples of calculating the amount of energy something uses based upon its power rating and how long it is turned on. And like I said in class, I like using analogies between volume of water, let's say, and energy. Because energy is kind of like a something. You just can't see it. But it's stored. You can store it. Kind of like you store water. Power is the rate of flow of that energy. Just kind of like if you have a gallon container and you're pouring it out. If you pour it out quickly, it comes out with a greater flow rate. That's similar to if you have a battery, you discharge it quickly. It's a greater flow rate of the energy. and that would be in watts. And here's an example of producing energy. We like to produce energy, right? That's why we have solar panels and wind farms and gasoline engines, for that matter. I like the alternative energy approach myself. So if something is producing a certain amount of power, a certain number of joules per second, and it's running for a certain number of hours, you can multiply that power rate by the number of hours, and it tells you how much energy it produces, kilowatt hours. You could talk about the same amount of energy that something, or electricity energy that something uses. Multiplying the number of watts times the number of hours gives you also the amount of energy something consumes. Here's some more examples of calculating energy from power and time. Let's say you have a 1,000-watt heater that you accidentally leave on for a week. How much electricity will it use during that time? So think about how much electrical energy will it use during that time. See if you can do this problem on your own. The next slide will show you the answer. What you're going to do is you're going to take the 1,000 watts and you're going to multiply it by the time, 7 days. But let's convert it into a unit that we can work with. So 1,000 watts is a kilowatt. Multiply it times the time, 7 days, times the number of hours per day, and you'll get your energy used in kilowatt hours, 168 kilowatt hours. Then if you want to figure out how much it's going to cost you, each kilowatt hour costs you 15 cents, about. It varies. We can talk about how much energy costs. It's going to change depending on where you're located, time of year, and other things. But if it's about 15 cents per kilowatt hour, you can figure out what this mistake of leaving your electric heater on for a week will cost you, besides the energy that you wasted. And it's about $25. Next, let's say you have a solar panel and you want to charge batteries, and that you need 100 watt hours of solar energy to charge your battery for the night, because you have 100 watt hours of batteries, let's say. If you only get 4 hours of sunshine, you could figure out how many solar panels you need. And without having any extra here, if you have solar panels that will deliver you 25 watts on the average, and you're running those solar panels for 4 hours per day, because that's how much sunshine you have, then you're going to get 100 watt hours per day. That's 4 hours times 25 watts, 100 watt hours per day. And that will be just enough to satisfy your needs. You might want to get a couple more just to make sure that you're over that. But this is how you can do the calculations to figure out how many solar panels you'll need or how many batteries you might need to accomplish something. And again, here's a reminder of the equations we've used thus far. Energy divided by time is power, and it's also equal to voltage times current. We'll talk more about units later, but this is your initial overview of it. Here's another question. See if you can answer it. And the next slide should give you the answer, I think. There we go. And just a reminder of what battery ratings are in that we just talked about a few minutes ago. Amp hours or watt hours. And here's a couple more questions. How many hours could a 14 amp hour battery deliver 2 amps of current? Well, 14 amp hours, divide that by 2 amps of current, and you get 7 hours. The solar suitcases that I have stored somewhere, use a 12-volt battery. They have a capacity of 14 amp hours. So what's the watt-hour rating of the battery? If it is a 14 amp hour capacity, but it's a 12-volt battery, well, you multiply those two, you get 168 watt-hours. And if you have lights, they draw 2.4 amps for 4 hours. Using the 12-volt batteries, how much energy would you need to operate them? Well, you figure out the number of amp hours, you multiply the amps times the number of hours, then you multiply that by the voltage of the battery, 12 volts, and you get the number of watt hours, how much energy that would be needed to operate those lights, those specific lights for that time period. This lecture's gone on for a while. We're at just about the last couple slides. But as a reminder, there's two equations that really we've talked about. That is that power is equal to current times voltage, and the units are watts for power, and amps and volts for current and voltage, of course. And then, of course, Ohm's law, that voltage is equal to current times resistance. You can rearrange these to solve different problems that you're going to have, but these are three basic equations that we'll find useful. And we're going to do a little bit more with this in the subsequent lectures and some examples of actually trying to do what we did earlier, figuring out how much energy we'd need to run a certain light for a certain period of time. Therefore, how many solar panels would we need? There's some design problems. And we can also start incorporating efficiency, given that solar panels are really only 20% efficient. We'll actually probably need a lot more solar panels than you might think if they were 100% efficient. We'll talk more about that. Okay,